Imagine building a house. You wouldn't start by randomly placing bricks. You need a plan, a structure to guide you. Similarly, in programming, data structures are the foundation upon which we build efficient and organized programs. They help us store and manage data effectively. Data structures provide a way to organize and access data in a computer's memory. Just like shelves in a library help us locate books, data structures provide efficient ways to store and retrieve information. Understanding data structures is crucial for any programmer wanting to write efficient and optimized code. Let's say you have a list of student names. Without a data structure, you would have to store each name in a separate variable, making it difficult to manage. With data structures like arrays or linked lists, you can store and access these names systematically. Whether you're developing a simple mobile app or a complex artificial intelligence algorithm, understanding how to choose and implement the right data structure can significantly impact your program's performance and scalability. In the following sections, we'll explore some fundamental data structures and their applications. One of the most fundamental data structures is the array. Think of an array as a series of neatly labeled boxes lined up next to each other. Each box or element can hold a piece of data, and you can access each element using its unique index number. Arrays are perfect for storing collections of data that are the same type, such as a list of numbers or a series of characters. Imagine you want to store the high temperatures for each day of a week. You could use an array with 7 elements, each representing a day of the week. Each element would hold the corresponding day's high temperature. Arrays provide a simple and efficient way to store and access this data sequentially. Let's say you want to find the temperature on the 3rd day of the week. You would simply access the element at index 2, remember arrays typically start at index 0, and you would have the desired temperature value. Arrays make it easy to perform operations on a group of related data. Arrays are used extensively in programming for tasks such as storing and manipulating collections of data, representing matrices, and implementing algorithms. Understanding how to work with arrays is essential for any programmer. While arrays are incredibly useful, they have limitations. For instance, inserting or deleting elements in the middle of an array can be inefficient, especially with large datasets. That's where linked lists come in. Imagine a linked list as a chain of nodes where each node contains data and a pointer to the next node in the sequence. Unlike arrays, linked lists don't require contiguous memory allocation, making them more flexible for dynamic data storage. Imagine you have a playlist of songs. You can add or remove songs from the playlist without needing to shift all the other songs around in memory. Now let's talk about stacks and queues. Imagine a stack of plates. You can only add or remove plates from the top. This is known as the LIFO, last in, first out principle. Stacks are used in programming for tasks like managing function calls and undo operations. Queues, on the other hand, operate on the FIFO, first in, first out principle. Think of a line at a grocery store. The first person in line is the first to be served. Queues are used in scenarios like handling requests in an operating system or managing print jobs. In this section, we'll dive into more complex data structures like trees and graphs. Trees are hierarchical structures that consist of nodes connected by edges. Each node contains a value and can have multiple children nodes. Trees are used in various applications such as representing hierarchical data, managing databases, and optimizing search algorithms. Imagine a family tree. Each person is a node, and their children are connected to them through edges. This structure allows for efficient representation and querying of hierarchical data. Now, let's move on to graphs. Graphs are collections of nodes connected by edges, where each edge can represent a relationship or connection between nodes. Graphs are used in social networks, transportation systems, and many other fields. For example, in a social network, each user is a node, and their friendships are the edges connecting them. Understanding how to traverse and manipulate these structures is crucial for solving complex problems efficiently. In the next sections, we'll explore breadth-first search, BFS, and depth-first search, DFS, two fundamental algorithms for traversing graphs. Now that we've delved into trees and graphs, it's time to explore two essential algorithms for traversing these structures: breadth-first search, BFS, and depth-first search, DFS. Breadth First Search, or BFS, is an algorithm for traversing or searching tree or graph data structures. It starts at the root node and explores all the neighboring nodes at the present depth, before moving on to nodes at the next depth level. BFS is particularly useful for finding the shortest path in unweighted graphs. Imagine navigating through a maze. BFS helps you explore all possible paths, level by level, ensuring you find the shortest route to your destination. On the other hand, Depth First Search, or DFS, is another powerful algorithm for traversing or searching tree or graph data structures. DFS starts at the root node and explores as far as possible along each branch before backtracking. This makes DFS ideal for tasks such as topological sorting, finding connected components, and solving puzzles. Picture solving a labyrinth by following one path as far as it goes before trying another. This is how DFS operates, diving deep into each branch before moving on. Both BFS and DFS are fundamental tools in a programmer's arsenal, each offering unique strengths and applications. Understanding when to use each can greatly enhance your problem-solving skills and efficiency. With BFS and DFS under your belt, you're now better equipped to tackle complex data structures and algorithms. In the next scene, we'll discuss why practice is crucial for mastering these concepts and how you can hone your skills effectively. In addition to trees and graphs, there are other advanced data structures that are essential for solving complex problems. For example, heaps are specialized tree-based data structures that satisfy the heap property, making them useful for implementing priority queues. Imagine a to-do list where the most urgent tasks are always kept at the top. This is where heaps excel. GAP2S. Hash tables are another powerful data structure. They provide fast insertion, deletion, and lookup operations by using a hash function to map keys to indices in an array. Think of a hash table as an efficient filing system where each document is quickly accessible based on a unique identifier. Understanding these advanced data structures and their applications will help you write more efficient and optimized code. With heaps, you can manage priority tasks seamlessly, and with hash tables, you can achieve rapid data retrieval and manipulation. Mastering these advanced structures not only broadens your toolkit, but also empowers you to tackle a wider range of computational challenges with confidence and precision. In the next scene, we'll discuss why practice is crucial for mastering these concepts and how you can hone your skills effectively. Stay tuned to this channel for solutions and detailed explanations of competitive programming questions from LeetCode. Don't forget to like, subscribe, and hit the notification bell to stay updated with our latest content. Data structures are the backbone of efficient programming. They provide a framework for organizing, managing, and manipulating data effectively. From simple arrays to more complex structures like linked lists, stacks, and queues, each data structure serves a unique purpose and comes with its own set of advantages and limitations. Understanding these fundamental data structures is crucial for any programmer, as it lays the foundation for writing efficient, scalable, and maintainable code. Just like a carpenter needs to master their tools, a programmer needs to be proficient in using data structures to build robust and high-performing applications. Practice is key to mastering data structures. Start by implementing basic data structures like arrays and linked lists from scratch. Then, move on to more advanced structures like trees and graphs. The more you practice, the more comfortable you will become with choosing the right data structure for a particular task and implementing it effectively.